As promised, today we were going to go through some more practical stuff with assembly programming. First and foremost is the programming environment for the microchip processor. And let's see here, your organization will open with Atmel Studio. Atmel Studio is built on top of Visual Studio. So if you're familiar with Visual Studio from programming with C++, it will be a familiar environment for you. It takes a minute to load up. And here is the template file. Let's go ahead and minimize this a little bit. But anyway, the template file is the file that I believe I put it on Canvas. Have I put it on Canvas? Yeah, okay. This is the file you start with to write your programs. It includes the vector interrupt vector table, which is a little lengthy. Then it has the start routine, which configures the clock, configures the interrupt vectors, and then just does a loop that does nothing. Okay, the interrupt vector table, let's start with, go through each section in order. The interrupt vector table contains jump commands. After a jump command, you put a label for where you want it to jump to. When an interrupt gets triggered, for example, the real-time counter overflow and compare match interrupt, when that interrupt gets triggered, it automatically jumps to this location, and then in turn jumps to wherever you are, wherever you point it to. That's built into the hardware. You can change it, but it changes to another location that's kind of confusing, so I just put the interrupt vector table at the start of the program. And it starts with a reset interrupt, which is at address 0. The address in program memory is not shown, but when you first start the processor and give it power, the address in the program counter is going to be 0, so it's going to go to this line here, jump start, and it will jump to the start label, which labels are text, no spaces, that has a colon after it. So it jumps to here, and it loads an immediate LDI for into register 26, the number hex 68, and loads into register 27, 00, hex 00. Then it loads into register 17, this bit mask. which selects the selects the clock to be, if in the register you're going to point it to be a 20 megahertz clock. So the processor will be operating at 20 megahertz after you execute the store command down here. Now the clock select register at 0068 is locked, so you have to unlock it using these two commands. It's one of those things where you lock a register. A register remains locked so you don't accidentally change it in your code. You have to put the unlock in there, write to it, and then it locks again like 4 or 5 clock cycles later. So this unlocks the register for 5 or 6 clock cycles. You can execute your store command, which takes the X pointer, which is pointing at 0068, and puts in the value puts in that location the value in R17, which is this binary number there. Yes?
Like, so I know we went past that, we were going over like different memory locations.
Yes.
With this here, why is it using those specific ones, like for starting the clock, and then when you're going into like with the unlock register, you said that was about 5 or 6 cycles.
Yeah.
What makes that go, and like what are we seeing inside of that makes that clock, like the cycle, the amount of times it's doing that?
One clock cycle is one line of code. So this command, these two commands unlock the register. So for this command, this command, this command, and so forth, for 5 or 6 4 or 5 clock cycles, that register is unlocked, and you can store a value in that register. So let me see here. We'll go to the clock controller. Oh, hush. Fine. Clock controller. And we'll have the register summary. The clock controller that we're going to use is the clock select. Oh no. But, let's see here. Peripherals and architecture. Clock control is 60. 0 hex 0060. That's your clock controller. And we're going to go to the register summary. We're going to go to 68, and which has the frequency select bits. And in the in this register here, the frequency select, we're selecting 20 megahertz. So we have a 1 in bit 5's location, because that's what hex 8 would be 1000. They do the offsets in and bit field descriptions in hex rather than binary. I don't know why. but that's the value that we're selecting, 20 megahertz for the clock select. And it is configuration change protection. That means it's locked, like I just described a little bit ago. So that's what's going on here. And then store in the 1 in the in bit 5's position. And then similarly, you configure the interrupt vectors, change the pointer of X from what it was up here to this down here. Select the appropriate bit that you want to select and have the interrupt vectors located at, which is interrupt controller, register summary, is that, what's the address? 0110. So, the address is the CPU interrupt controller, 0110. Go to the CPU interrupt controller, the register summary. Offset 0 is control A. Control register A. Interrupt vector select in the 1 in that bit location sets the interrupt vectors at the boot section of the flash, the first addresses to run in the program. So that, again, it's a locked register, so you have to do this command to unlock the registers, these two commands, and then you can store the value in R17 at that register's location. Then the loop, after it does that, it does no operation, NOP, and does a relative jump to loop, NOP, R jump to loop, and just goes on forever. So the template program doesn't have any functionality to it. It just configures the clock and the interrupt vectors. Now we have this program, which is the first programming project. The interrupt vector table, all the interrupts that that the processor has are set to start, so they don't. So if they get tripped for some reason or other, it's like rebooting the computer. It starts from 0, except for the timer counter A overflow interrupt. Okay, what does that mean? Go back to here. The timer counter A, 16-bit timer counter A, Let me see if that, does that increase the size at all? No. To it. Is that better? A little bit easier to read. It is a 16-bit timer counter. It has 3 compare channels, and it can be triggered as an interrupt. It can trigger an interrupt by using the overflow, which means the counter rolls over from the max number to 0 again, like an odometer on a car rolls over to 0 if it goes past, at least it used to. If it goes past 100,000 miles, you would roll over to 0. That is an overflow. So the timer counter has 3 compare registers. You can have values in the compare registers to trigger an interrupt if the value in the timer is equal to the compare value. So basically, the timer counter consists of a number from 0 to 16 ones, which is what is that? 8 or 9 billion or something like that. I don't remember. But no, that would be 32-bit. Anyway, up to hex FFFF, because it takes up to the compare and overflow registers contain a 16-bit number. So each clock cycle, or each scaled clock cycle, the counter increases by 1. And if it matches the overflow or the compare value, it triggers an interrupt if those interrupts are enabled. So, how do you use a timer counter? Well, functional description, initialization. To start using the timer counter in a basic mode, you write a top value to the period register. That's the value that it overflows at. It counts up to that number and then rolls back over to 0, triggering an overflow. Okay? It makes the period of the timer. Enable the peripheral by writing a 1 to the enable bit in control register A. The counter will start counting clock ticks according to the prescaler setting in the clock select bit field of timer counter A, control A. Optionally, by writing a 1 to the enable counter event input A bit in the event control register, events are counted instead of clock ticks. So you can have it used as a counter that, say, you have pulses coming in from a pin, it can count those pulses. So that's why it's a timer counter. It can count incoming signals, or it can go off the clock and be a timer that way. The counter value can be read from the counter bit field in the counter register. To initialize interrupts, it has four interrupts, sorry. Overflow, compare 0, compare 1, and compare 2. So if you have the interrupt control here, you can trigger, you can initialize, set the OVF bit to 1. If you're using the compare 0, you can use put a 1 in there. Compare 1, compare 2. Likewise, you can count up to different numbers. You set those numbers in the period and compare registers. Period, compare 0, compare 1, compare 2. The count is where it registers, or is where the counter number resides. So it compares the counter register to the period register, the compare register, whatever, all of them actually, and triggers interrupts accordingly. Now back to the program. When you're initializing the went through the okay, configuring the timer counter type A 0. The base address for the timer counter 0 is 0x0A00. So you load in register 26 and 27, those numbers, and then you configure the clock select. You I believe the clock select is that shouldn't be right. It should be more than that. It should be divide by 1024. So value in this bit field here should be 7 or 111. So that should be 111 there. And then store that value in register 16 into the address pointed to by X. Then set the appropriate interrupt enable bits. The overflow bit is all you're going to be using in this program. So you write the offset in register 26 and then store the period, the pointer X in that location, the value in R16. Then you set the global interrupt enable bit. You have to enable interrupts on a global level in order for any interrupts to be able to be triggered. That is done with the SEI command. Finally, enable the timer counter, which is the I don't know, but this is supposed to be the blinking light example, blinking a light every second, but this is not. Hmm. Anyway, we'll enable the timer counter by going back to the Control A register again, which has the enable bit here, bit 0, and our clock select was at 111. So this this should be 0B00001111, and load that into the address pointed to by X, which is that control register of the timer counter. Too much, too fast? No? Following along? Kind of? Huh? Okay. Where did I lose you?
Hey, I'm just getting an understanding of like what this individual thing is. I think for me, what I'm having a hard time, like for watching is like, I don't know, I guess like the reason, because like we're asked to do this, like I'm not understanding
Okay.
what's all right. I get what each individual thing is doing, but I'm having a hard time understanding how to put this into a program of what is actually happening as the program is.
At this point, it's just what I've. The only thing I've covered here is just configuration, setting things up. And like I said, rather than
You configure in the light switch?
No.
The bulb or you
The-
configure in the chip?
the timer in the chip. That's all that was. Like I said before, I made no secret of it. Assembly is very tedious. It has, you have to do, a dozen lines of code just to do one little thing you would do in C. This program in C++ is what, 4 lines? Turn the light on, to delay, turn light off, delay, and then loop. Okay. This program, this is an incomplete program. But the complete program is like 250 lines of code. Yeah. So, yeah, it's, I mean, there's white space in there and comments, but still, you take all that out and you'd still be with, you'll still have, 150, 200 lines of code. Just to blink a light on and off once a second. This is why people don't like assembly code.
So,
I can see
and
that.
You're already not liking it, right?
Is this like a, would this be, since this is the setup part, or would it just be, like, do we use the same, like we're using I think they're being located to certain spaces. Will we be using that for any program aside from changing like where we, I think it's, what is it, where the actual bid that we put in the bid for that? Like, is that the only thing that we would change? So like, we would be continuously using this inside of, even if it wasn't to turn on and off a light, right? This is just the setup portion of it.
If you're going to use the timer counter, this is the setup portion that you would use all the time. If you're not going to use the timer counter, you can erase that. Theoretically, the third programming project doesn't use the timer counter, so you wouldn't use the timer counter setup.
So with this, would you say it's pretty good for us to, as we, like how you were referring to our manual, would you say it's a good idea for us to keep like inside of this, utilizing this to go, even though there's different ones, like different codes, I guess, or lines, would you recommend us just utilizing going back to the AVR manual?
AVR manual back and forth a lot. Yeah. Because on the hardware level, there's a lot of options and that sort of thing, and a lot of information. I mean, it's, all those registers, each line is a register. All those registers just to control the timer. And there's what, 4 timers of this type. So if you're using different timers, you have to configure all this stuff manually. You can't just say copy configuration from timer counter A to timer counter A0 to timer counter A1.
Guess that's kind of like, so inside of that part of it, kind of like refers into like where you were talking about specific one, like inside of it.
Yes.
That's what will help us decide what register we are utilizing.
Yeah, you could use. This is for time. This program that I was showing you is for timing. Timing. In this case, the blinking of a light. It could be timing of the second hand on a clock. Give it a tick every second, kind of a thing. But the different, depending on how you're using the timer counters, it's you would configure them differently. But at the hardware level, all these control registers and data registers give you ultimate complete control over the timer. So any way it can be possibly used is right there. It's right here in the register descriptions and this whole chapter, really. Timer counter A from page 211 to what is it? What's the from 211 to 259? So that's 48 pages to describe how the timer works. And that's just one of the peripherals. Yeah, to use the timer counter, you don't have to read all 48 pages. Just get the idea of what a timer counter is, and pick and choose. That's one thing I'm hoping to convey to in this class is how to read a data sheet like this. You have to pick and choose what you're reading. You don't want to waste time reading about the electrical characteristics based on temperature variations of a pin, when it's going to be operating at room temperature. You don't care. It should be just fairly normal. You're not putting this in an extreme environment, so you don't care. So you can skip all that. But on at the base level, let me pull up the timer counter. Is 2 registers. Count low and high. And a input signal. That's basically all it is. Everything else is just icing on the cake. The 2 registers, you just count. It just counts the input signals coming in. And it just counts up. It doesn't count down. It only counts up. Yeah, and when it gets to its maximum value, it rolls back over to 0. Okay? Now the input signal can be a pin or the CPU clock. In the case of a blinking LED, it's going to be the CPU clock. But the thing is this is where it get into configuration a little bit. The CPU clock operates at 20 megahertz. Somebody have a calculator handy? Scientific would be nice. Okay. 2 to the 16th power. At 64,000. Yeah, 65,535 is what it would count up to. So 65,535 is as high as it'll count, and then it would overflow. Okay. It would do that several times a second at 20 megahertz. Many times a second. Because that's 20 million cycles, pulses every second. So you have a prescaler. And for this program, we set that to 1 over 1, 0 to 4, 1024. To slow the input signal down so it can be used in a human readable form, human readable speed.
That like a second?
Yes, 20 million per second is the clock speed. So CPU clock is 20 megahertz. So divide it by, use the prescaler to divide it by 1024. What's 20 million divided by 1024? $19,531. So that makes it 19,531 hertz. Now that number, that 19,531 is less than 65,535. So you can set the period register of the clock at that speed, at that number, and it will trigger an overflow every second. Anybody have a scientific calculator that can convert to binary? If it's a TI, it's not. TIs for some reason or other have not put number conversions on base conversions on their scientific calculators. But convert this number to convert this. You would convert this number into binary and set that as your period register, and have it overflow every second. And we are out of time. It is 2:51. So we'll continue with this on Monday. Hopefully we'll have more of an audience, get more questions. I do welcome questions. If you're not getting it, I'm not conveying it well, please let me know. I'm not going to hold it against you. If nothing else, I'm going to thank you for it. Teaching assembly is not. Teaching assembly is a different type of monster because it is so different. It doesn't have all the handy dandy functionality of like for loops and objects and variables and all that sort of stuff that C++ and other languages have. So teaching it is a learning process for me as well, because how to convey this properly is challenging because it is a challenging language, and it challenging because of its simplicity, if that makes sense. But anyway, have a good day, have a good weekend. See you on Monday.